Good morning. In this part of the course, we continue our study of two-port network parameters by introducing hybrid parameters, commonly called H parameters. The H parameter representation is particularly useful for modeling electronic devices and transistor circuits because it combines voltage and current variables in a convenient form. We will first define the H and G parameter sets, and then apply the H parameter formulation to several transistor models. This part begins with a brief review of the two-port network. We then introduce the hybrid parameters and their dual form, the inverse hybrid or G parameters. After establishing the definitions, we will study three applications. The first is the common emitter transistor. The second is a simplified model of a bipolar junction transistor. The third concerns the small signal model of a field effect transistor. The objective is to show how the general two-port definitions can be used to derive practical device models. Let's begin by recalling the two-port network. The network has two ports with the voltage and current variables V1 and I1 at port 1 and V2 and I2 at port 2. The H parameter representation relates the input voltage and the output current to the input current and the output voltage. This mixed choice of variables is the origin of the name hybrid parameters. The corresponding inverse representation is described by the G parameters. The H parameters are defined by a 2x2 matrix equation. The first equation expresses V1 in terms of I1 and V2. The second expresses I2 in terms of I1 and V2. The four parameters are obtained from specific test conditions. The parameter H11 is the input impedance with port 2 short-circuited. The parameter H12 is the inverse voltage ratio with port 1 open-circuited. Similarly, H21 is the forward current ratio with port 2 short-circuited, and H22 is the output admittance with port 1 open-circuited. The inverse hybrid parameters, or J parameters, use the complementary arrangement of variables. Their definitions are obtained by interchanging the rows of voltage and current at the two ports. We now begin the first application, determining the H parameters of a common emitter transistor model. Our objective is to express the two-port variables in the standard H parameter form, V1 as H11 I1 plus H12 V2, and I2 as H21 I1 plus H22 V2. We will derive the four parameters directly from the transistor equivalent circuit rather than converting from another parameter set. We start by applying Kirchhoff's current law at node D. The resulting equation relates the node voltage Vd to the input current I1 and the output voltage V2. Solving this equation for Vd gives a linear combination of I1 and V2. This intermediate result is the case step in the derivation because Vd can now be substituted into the equations for both the input voltage and the output current. We now determine the input voltage. From the circuit, V1 is equal to the node voltage Vd plus the voltage drop across the base resistance, which is Rb I1. Substituting the expression previously obtained for Vd gives V1 directly in terms of I1 and V2. By comparison with the first H parameter equation, we immediately identify H11 as the input impedance term and H12 as the reverse voltage ratio. We next determine the output current. Using the transistor model, I2 is expressed in terms of the transistor current contribution and the current through the emitter resistance. Substituting the previously derived expression for Vd gives I2 as a linear combination of I1 and V2. Comparing this result with the second H parameter equation allows us to identify H21, the forward current gain, and H22, the output admittance. Combining the results obtained for the input voltage and output current gives the complete hybrid matrix of the common emitter transistor model. The four elements have clear physical interpretations. H11 is the input impedance in ohms. H12 is a dimensionless reverse voltage gain. H21 is the dimensionless forward current gain. Finally, H22 is the output admittance in Siemens. This example illustrates the main advantage of the hybrid representation. The parameters can be obtained directly by comparing the circuit equations with the standard each parameter equations. We now completed the derivation of the each parameters for the common emitter transistor model. The procedure we followed is general. Write the circuit equations, eliminate the internal variables, and express the port variables in the standard hybrid form. We will now apply the same methodology to another transistor model, allowing us to see how the each parameters emerge from a different equivalent circuit. We now consider a simplified small signal model of a bipolar junction transistor. Our objective is again to determine the four hybrid parameters directly from the equivalent circuit. The circuit contains the base emitter resistance and capacitance together with the controlled current source representing the transistor transconductance. We will use the H parameter definitions and apply the appropriate open circuit and short circuit conditions at the output or input port. For this simplified BJT model, the input port contains the parallel combination of the base emitter resistance and capacitance. With the output port short-circuited, the input impedance is therefore determined by this parallel combination. The reverse voltage parameter is 0 because there is no direct feedback path from the output voltage to the input port in this simplified model. The forward current parameter is the transconductance multiplied by the input impedance, while the output admittance is 0 in the idealized model. Thus, the H matrix follows directly from the circuit topology and the four defining conditions. We now move to the third example, the hybrid parameters of a small signal FET model. The model includes the input resistance, the gate source and gate drain capacitances, the drain source resistance, and the controlled current source with transconductance Gm. For this example, we will first write the two-port equations directly from the circuit. We can then rearrange them into the standard each parameter form and evaluate the parameters numerically at the specified frequency. We begin with the gate current I1. The current consists of three contributions: the current through the input resistance, the current through the gate source capacitance, and the current through the gate drain capacitance. Similarly, the drain current I2 contains the controlled current source contribution, the current through the drain source resistance, and the current through the gate drain capacitance. After collecting the terms multiplying V1 and V2, both port currents are expressed as linear combinations of the two port voltages. These equations provide the starting point for determining the hybrid parameters. We now apply the standard definitions of the each parameters. The first parameter, H11, is obtained with the output port short-circuited, so V2 is 0. The reverse voltage ratio, H12, is obtained with the input port open-circuited, so I1 is 0. Similarly, H21 is the forward current ratio under the output short-circuit condition, while H22 is the output admittance under the input open circuit condition. By applying these four conditions to the port equations, we can obtain closed-form expressions for all four hybrid parameters. The closed-form expressions obtained from the circuit equations are summarized here. The input hybrid parameter H11 is the reciprocal of the total input admittance formed by the input resistance and the two capacitances. The reverse parameter H12 is determined by the gate drain capacitance and the same input resistance. The forward parameter H21 is obtained by multiplying H1y by the effective transconductance term, while H22 includes the drain source conductance together with the capacitive feedback and transconductance contributions. Using the given numerical values as 5 GHz, these expressions can now be evaluated to obtain the complete complex hybrid matrix. Finally, substituting the numerical values into the closed-form expressions gives the complete hybrid matrix of the FET model at 5 GHz. The matrix entries are complex because the capacitors introduce frequency-dependent reactive terms. The result illustrates an important point. Even when the physical circuit elements are simple, the hybrid parameters may be complex and frequency-dependent. We have therefore completed the three examples of the hybrid parameter extraction. In each case, the same general procedure was followed. Write the part equations, apply the appropriate defining conditions, and identify the for each parameters. This concludes our study on hybrid parameters.